Hey, hello there. So today's Leetcode challenge question is called possible bipartisan. We have a set of n people numbered from 1 to n. We would like to split those people into two groups. Each person may dislike some person, so they will fight each other if they were assigned to the same group. So for that reason, we want to separate them. Formally, this dislike relationship is a list of tuples, where the tuple is the pair of person that does not go along with each other. So this is in the form of edge list. It's going to be a little bit inefficient to enumerate over when we try to traverse through the graph here. So yeah, every person here is a node in the graph. The edges are the dislike relationships. And we want to determine whether we can split everyone into two groups this way. So it's a true or false testing. So yeah, let's look at this as an example. The last one is a little bit longer, so it might show the idea a little bit clear. So the idea is that for the graph, bi-party graph kind of problem is try to assign the nodes into two groups. So let's say we have a party 0 and party 1. So when we were actually exploring this graph, traversal through this graph, when we find a node, let's say node 1, person 1, we just want to randomly throw it into one of the party there. And since that 1 does not like person 2, we put person 2 in the opposite party. And then we notice that the person 2 does not like person 3, so we put person 3 onto party 0. Person 3 does not like person 4, we put person 4 into the opposite party. And 4 does not like 5. And 5 does not like 1. So we were attempting to assign person 1 into party 1, but person 1 already being assigned to party 0. So this conflict shows us there's no way we can do this bipartisan split on this particular graph. Yeah, so the idea is just in two steps. We want to convert a graph edge list to adjacency list for faster traversal inside this graph. Otherwise, we would go in here and find that the node we are looking at is one of the node there, and look up at the the person that he dislikes. If we have an adjacency list for person 1, I will have a list to collect the person that he does not like. For any person, I will collect the person he does not like. So the traversal through this graph will be much efficiently, and also the person number can be used to access that list. So it will be much efficient, and this conversion will be would take up a number of edges in space. And since that we're converting the entire edge list into this adjacency list format, it will take the time that's linear with respect to the number of edges. The second step is to do this party assignment. We do this component by component. So we want to make sure that we can since that the graph can contain multiple isolated components, we want to make sure that we visit every component. And within the component, this dislike kind of relationship has to be checked. But across different components, that doesn't matter, because there's no person dislike the person from the other component. So it doesn't really matter the entry point, how we assign people within this component when we concerning about the other group. It doesn't really matter. But within this group, we need to put the person that dislike each other into the opposite party. So this, we definitely want to visit every node at least once. So the time is node plus edges. Because for every person, we want to check the person he dislike, either to do assignment or do violation checking. So it's node plus edge. And in terms of time, in terms of space, we will want to have hash table to store the assignment, the party belonging kind of thing. So it's order of nodes, and also when we're doing the traversal, the size of the stack or queue depends on whether you're doing DFS or BFS. It's going to be the same size as the component, which can potentially be the entire graph. So it's potentially order of n. So that's the time and space analysis. With that out of the way, I will start coding this question. So we'll have a adjacency list. Which is going to be of size n plus 1, because we're starting with 1 as the index. So we want adjacency list brackets 1 is going to be the list of people that person 1 does not like. It's an undirected graph, so if person A does not like person B, then person B does not like person A. So it's bi-direction. So that's the graph pre-processing part, and then we should start this graph traversal piece. So we will have a integer to indicating the graph party assignment, and then we're just gonna make sure that we iterate over all the nodes. If we haven't visited the node I yet, it means that it's now our entry point to this component. But if we have already assigned the node a party, that means we have already visited that component, so we can skip that node entirely. So otherwise, we will use that entry and the node as the entry point to just start a tow along inside that connected component. For this particular entry node, we want to assign it to a party, and it doesn't matter which party we assign it to. So just randomly put it into this the zeros group. So we're gonna have a tow. Initially, just this entry node. If it's empty, if this node is isolated, we'll exit this just in one iteration. Otherwise, as long as we still have nodes that in the component, we want to keep exploring. So whether we do DFS or BFS, it pretty much in this iterative version just depends on do we pop the front or pop the back. So since I'm popping the front, I'm doing BFS. Yeah. So for this node, we want to look up its enemies and put the enemy into the other, into the opposite party. Let's call this A. So here we definitely want to do something that's to put this B into the opposite party. That's when the person B does not have a party yet, so we can safely assign it to the opposite party. And the case that when we don't know the party where B belongs to also suggests that we haven't processed this node yet, this person yet, so we need to push it back to this tow. So after we've done that, we make sure either if we don't enter this if condition, that means B already have a party, or otherwise we have already assigned it a party. So we can just check if the party is equal to A's party, that means we have a violation. the two enemies are in the same group, so it's gonna starting a war every single class. So that's pretty much this checking here. So after this for loop, we should be able to safely say that we truly can, you know, actually split the peoples into two groups without any fighting. Yeah, that seems to be the code. Let's quickly check. The adjacency list is the person mapping to associated with the person that he does not like. We're converting the edge list into that, which is processing every single edge in this graph, and that adjacency list would take up space. Yeah, I think the space is you could say it's node plus edge or just edge itself. It shouldn't be too much of a problem. Then we start to explore this graph component by component. If we haven't given the node a assignment yet, that means this is the entry node to this component. We will start a toe inside that component. Depends whether we want to do pop front or pop back. It's DFS or BFS, which doesn't matter in this case. They're equivalent because we have to explore this graph this components entirely, and we don't really know whether BFS will terminate earlier or DFS will terminate earlier. Yeah. So yeah. So for each pairs of person, for every person that we're looking at, we try to look at its enemies, and we always want to assign the enemy into the opposite party. If we do find that we have two enemies ended up in the same group, we should return false. Okay, let's see if it's working. Alright, so yeah, that's this question for today. It's a graph problem into two steps, the pre-processing and the graph traversal. Yeah, so that's pretty much it.